The morning of April 9th, 1942, and Captain Takeshi Hara stood in a dusty testing yard outside the Mitsubishi Heavy Industries facility in Nagoya, staring at something that shouldn't exist. The vehicle in front of him was a Willys Jeep, one of 11 captured during the fall of Bataan 3 days earlier. American markings still visible under the tropical grime. Serial number stamped on the dashboard, technical manual stuffed in the canvas pouch behind the driver's seat. Hara had been ordered to evaluate this machine, measure it, test it, determine how the Americans were building light reconnaissance vehicles, and whether Japan's own Type 95 Kurogane needed modification in response. But already, before he'd even started the engine, something felt wrong. The vehicle was too light, too simple, too crude in its construction, and, according to the technical manual sitting in his hands, it claimed capabilities that violated everything Hara understood about automotive engineering. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The manual specified a payload capacity of 660 pounds, standard enough for a light reconnaissance vehicle. The Kurogane, Japan's only indigenous four-wheel drive scout car, could manage roughly the same, though its 33 horsepower engine struggled with anything approaching that limit on difficult terrain. But the manual also included field reports, hastily translated notes from American maintenance logs found with the vehicle, and those notes described something impossible: jeeps routinely hauling 1,200 pounds of cargo. Some reports mentioned loads exceeding 1,500 pounds, ammunition cases, fuel cans, water containers, extra personnel, loads that should have destroyed the rear axle within miles. Hara checked the math 3 times. The Jeep's curb weight was listed at 2,200 pounds. A 1,200-pound payload meant the vehicle was operating at over 150% of its empty weight. The rear axle, a Dana 27 with what appeared to be simple carbon steel housing, should have cracked under that kind of sustained stress. The suspension, basic leaf springs with no progressive rate design, should have bottomed out constantly. The frame, a simple ladder construction welded from mild steel channel, should have developed fatigue cracks within weeks of that kind of abuse. Yet, according to these field reports, Jeeps were doing this work day after day across North Africa, across the Philippines, across every theatre where American forces operated. Either the reports were propaganda, deliberate misinformation designed to deceive any Japanese intelligence analysis, or American automotive engineering had achieved something Japan's best manufacturers couldn't replicate. Hara didn't know which possibility disturbed him more. He walked around the Jeep slowly, taking measurements. Overall length, 132 inches. Width, 62 inches. Height, with the canvas top erected, 69 inches. Wheelbase, 80 inches. Ground clearance, 8 3/4 inches. Every dimension confirmed what the manual stated. This was not a large vehicle. The Kurogane was actually slightly smaller, measuring 129 inches long with a 70-inch wheelbase, but it weighed only 2,420 pounds, fully equipped. The American Jeep, despite being slightly larger, weighed less. That meant the Americans were either using lighter materials, which seemed unlikely given the crude stampings and heavy-gauge steel evident in the construction, or they'd found ways to eliminate weight without sacrificing structural integrity. Hara opened the hood. The engine was a Willys L-134, a 2.2-litre inline-4 designated the Go Devil, displacement of 100, 34 cubic inches, rated output 60 horsepower at 4,000 RPM, torque rated at 105 pound-feet at 2,000 RPM. Hara did the conversion to metric in his head. The Kurogane's air-cooled V-twin produced 33 horsepower from a 1.4-litre displacement. The American engine, from only 0.8 of a litre more displacement, produced nearly twice the power. That suggested either significantly higher compression ratios, which would require better fuel than Japan could reliably supply to field units, or superior metallurgy in the engine block, and pistons allowing higher operating temperatures and pressures. He examined the engine block closely. Cast iron, conventional in appearance. The pistons, visible when he removed the valve cover, were aluminum alloy, nothing exotic. The carburetor was a Carter unit, simple single-barrel design. The ignition system used a basic distributor with mechanical advance. There was no technological magic here, no secret American innovation that explained the power output. Just straightforward engineering executed with apparently superior materials and manufacturing precision. The transmission was a Warner Gear T84, a 3-speed manual with a single dry-plate clutch. Hara had seen similar designs in Japanese commercial vehicles. The transfer case, a Spicer 18, provided high and low range with front-wheel engagement. Again, nothing revolutionary. The Kurogane used a similar system, though the Japanese version required manual hub engagement at the front wheels, while the American version appeared to engage the front drive shaft directly through the transfer case. But it was the axles that truly confused him. Front axle, a Dana 25 with open differential. Rear axle, a Dana 27, also with open differential. Both used simple semi-floating designs, where the axle shafts bore some of the vehicle's weight. This was the weakest, cheapest type of axle design possible. Commercial trucks and heavy-duty vehicles used full-floating axles, where the shafts only transmitted torque, while the housing supported all the weight. Semi-floating axles were fine for light passenger cars operating on paved roads, but for a military vehicle expected to operate off-road, to climb obstacles, to handle combat loads, semi-floating axles should fail constantly. Yet here was this Jeep, captured after months of hard service in the Philippines, showing no signs of axle distress. Hara crawled underneath with a flashlight, inspecting the rear axle housing for cracks, deformation, or repair welds. The housing was original, unbent, unbroken. The differential cover showed scrapes from rock impacts, but no structural damage. The leaf springs, mounted directly to the axle with simple U-bolts, showed normal wear patterns but no indication of overload failures. This didn't make sense. Either the Americans had developed vastly superior steel alloys that looked identical to ordinary steel but possessed dramatically better material properties, or they'd discovered manufacturing processes that enhanced strength without requiring exotic materials, or the field reports were simply wrong and Jeeps weren't actually carrying the loads claimed. Hara needed to test the vehicle. Numbers on paper meant nothing. He needed to see what this machine could actually do. The testing protocol was straightforward. Load the Jeep to its rated capacity, 660 pounds. Drive it across the obstacle course Mitsubishi used for evaluating the Kurogane. Monitor for mechanical failures, excessive strain, handling degradation. Then, if the vehicle survived, incrementally increase the load until something broke. That would establish the true limits of American engineering. Hara assembled a testing crew. 2 mechanics from the Mitsubishi Motorsport, a technical writer to document everything, and a photographer to record any failures. They loaded the Jeep with sandbags, carefully weighed and stacked in the cargo area. 660 pounds, exactly as specified. The rear suspension compressed noticeably but not excessively. Ground clearance at the rear bumper dropped to roughly 6 inches, still adequate for moderate off-road work. Hara climbed into the driver's seat. The interior was Spartan. 2 bucket seats in front, a bench seat in back that folded flush with the floor to create cargo space. The steering wheel was simple, tubular steel wrapped in rubber. The instrument panel held 5 gauges: speedometer, fuel level, oil pressure, water temperature, and an ammeter. A voltmeter would have been more useful, but the Americans apparently preferred measuring current flow. The pedal layout was conventional: clutch, brake, accelerator from left to right. The shift pattern for the transmission was marked on the gear lever knob: first, second, third forward, reverse. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The transfer case lever sat to the right of the transmission, with positions marked H, N, L for high range, neutral, and low range. A separate lever engaged the front-wheel drive. Hara started the engine. It caught immediately, settled into a rough idle at about 600 RPM. louder than the Kurogane's air-cooled engine, but not objectionably so. He engaged the clutch, shifted into first gear, released the clutch. The Jeep rolled forward smoothly despite the 660 pounds of sandbags in back. First gear provided strong low-speed torque, as expected from the low numerical gear ratio. He drove toward the obstacle course at moderate speed, shifting through second and into third gear. The engine felt strong, responsive, with none of the hesitation or flat spots that plagued the Kurogane when loaded. The steering was direct, requiring more physical effort than a passenger car, but providing excellent feedback from the front wheels. The suspension handled the loaded weight well, absorbing bumps without harshness or excessive body roll. The obstacle course began, with a series of simulated shell craters, depressions 18 inches deep with steep exit angles. Hara approached the first crater in second gear, descended into it, then accelerated up the far side. The engine pulled strongly. The rear wheels bit into the loose soil without excessive spinning. The Jeep climbed out of the crater with no difficulty. He continued through 3 more craters, varying his approach angles and speeds. Every time, the Jeep performed flawlessly. Next came the log obstacles, pine logs 8 inches in diameter laid across the course to simulate fallen trees or large branches. Hara shifted into low range, engaged the front-wheel drive, and approached the first log slowly in first gear. The front wheels contacted the log, and the Jeep's momentum carried it up and over with minimal throttle input. The short wheelbase meant the rear axle hit the log almost immediately after the front cleared it, but the suspension absorbed the impact without bottoming out. He crossed 4 more log obstacles, each one requiring the vehicle to articulate over uneven terrain while maintaining traction. The Jeep's independent operation of front and rear axles, combined with the flexible leaf spring suspension, allowed it to maintain wheel contact even when the chassis twisted significantly. The Kurogane, with its more rigid suspension tuning, would have lifted wheels off the ground in similar circumstances, reducing traction and increasing the risk of getting stuck. The course concluded with a steep hill climb, a 30% grade covered in loose gravel. This was the test that always revealed weaknesses in drivetrain or engine power. Hara stopped at the base of the hill, ensured low range was engaged, and started the climb in first gear. The engine laboured but didn't stall. The rear tyres spun briefly on the loose surface, then found grip. The front wheels pulled the Jeep upward, distributing the load between axles. Halfway up, the rear end began to slide, laterally as the tyres lost traction. Hara corrected with steering input, maintaining momentum without excessive throttle that would have broken traction completely. The Jeep clawed its way to the top of the hill, engine still running smoothly, transmission and transfer case operating without grinding or slipping. At the summit, Hara stopped and shut off the engine. The testing crew walked up the hill to inspect the vehicle. No visible damage, no leaks from the axles, transmission, or transfer case. No overheating. The engine had maintained normal operating temperature throughout the test, despite the sustained load. They returned to the testing yard and unloaded the sandbags for inspection of the suspension and axles. Hara crawled underneath again with his flashlight, examining every component for signs of strain or imminent failure. The leaf springs showed no cracking at the mounting eyes. The shackles moved freely without binding. The axle housings remained straight and undamaged. The U-bolts securing the springs to the axles were still tight. This was beyond unusual. This was impossible. The Kurogane, when loaded to its rated capacity and driven over that same obstacle course, typically showed signs of strain. Spring eyes would elongate slightly. U-bolts would require retightening. The rear axle housing would develop small stress cracks near the differential, requiring welding repairs every few hundred miles of hard use. But the American Jeep, carrying the same load over the same terrain, showed absolutely no distress. Hara made a decision that would have consequences he couldn't foresee. He ordered the crew to reload the Jeep, but this time with 800 pounds of sandbags, 20% over the rated payload. If the vehicle was going to fail, this should trigger the failure. The mechanics stacked the additional weight into the cargo area. The rear suspension compressed further, ground clearance at the bumper now down to about 4 inches. Not ideal, but still functional for moderate terrain. They repeated the obstacle course. The Jeep handled differently with the heavier load, the rear end squatting more during acceleration, the body roll increasing during turns. But it still performed. It still climbed the hill. It still crossed the log obstacles. The engine temperature rose slightly higher, approaching the upper range of normal, but never entering the danger zone. And when they inspected the vehicle afterward, there was still no damage, no cracks, no loosened bolts. No signs that the machine was operating beyond its design limits. Over the next 3 days, Hara methodically increased the payload: 1,000 pounds, 1,200 pounds, 1,400 pounds. At each level, he drove the obstacle course, and at each level, the Jeep survived. The handling degraded progressively, the rear suspension nearly bottomed out with 1,400 pounds aboard, but nothing broke. At 1,500 pounds, more than twice the rated payload, the Jeep finally refused to climb the gravel hill. The engine had sufficient power, but the rear tyres couldn't maintain traction on the steep grade with that much weight compressing the suspension. But even loaded to 1,500 pounds, the axle housings didn't crack, the frame didn't bend, the suspension components didn't fail. Hara pulled the Jeep off the course and conducted a detailed metallurgical inspection of the rear axle housing. He removed it from the vehicle entirely, cutting sample sections from the housing for spectrographic analysis in Mitsubishi's materials laboratory. The results came back 3 days later. The axle housing was made from carbon steel, composition roughly 0.4% carbon, 0.7% manganese, trace amounts of silicon and phosphorus. Completely ordinary steel, not tool steel, not chromium steel. Not any exotic alloy that would explain superior strength, just plain carbon steel of the type Japan produced by the millions of tons annually. Yet this ordinary steel, formed into a semi-floating axle housing of minimal weight, had just survived loads that should have destroyed it. Hara wrote his report on April 22, 1942. His conclusions were carefully worded, but the implications were clear. Either the American field reports were deliberately exaggerated propaganda, or American manufacturing processes produced ordinary materials with extraordinary properties, or Japanese engineering understanding of material stress and failure modes was fundamentally incomplete. None of these possibilities reflected well on Japanese military intelligence or industrial capability. The report went to Major General Tomoyuki Yamashita, who commanded Japanese ground forces in Southeast Asia. Yamashita read it twice, then summoned Hara to his headquarters in Singapore. The meeting lasted 4 hours. Yamashita wanted every detail, every measurement, every test result, and most importantly, Yamashita wanted Hara's professional opinion, not as an engineer following orders, but as someone who understood what these results meant for Japan's war effort. Hara spoke carefully. The American Jeep represented a synthesis of ordinary technologies executed with precision that Japan's industrial base couldn't match. Every component was simple. Every design choice favored manufacturability over sophistication. There were no advanced features, no complex systems, nothing that required cutting-edge metallurgy or exotic materials. But every component was made well. Tolerances were tight, surfaces were finished properly. Materials were consistent. That consistency was what Japanese manufacturing couldn't achieve in 1942. Japan could produce excellent machinery in small quantities. The Zero fighter was proof of that. Individually crafted by skilled workers, each Zero was a masterpiece of lightweight construction and engine performance. But Japan couldn't mass-produce quality. Couldn't maintain tolerances across thousands of units. Couldn't ensure that the steel in axle housing number 5000 was identical to the steel in axle housing number 1. America apparently could. The Jeep Hara tested wasn't a prototype. It wasn't a specially built evaluation vehicle. It was a random production unit, one of thousands rolling off assembly lines in Toledo, Ohio. And it performed flawlessly because every Jeep rolling off that line performed flawlessly. That was the terrifying implication. America had industrialized quality itself. Yamashita asked the question Hara had been dreading. How many Jeeps could America produce? Hara consulted his notes. The Willys Overland factory in Toledo was designed for automotive mass production. Current reports suggested they were completing one Jeep every 90 seconds during peak production hours. Running 2 shifts, that meant roughly 700 Jeeps per day from that single facility. Ford Motor Company had also been contracted to build Jeeps under license. Their Willow Run plant, designed for bomber production, could theoretically match or exceed Willys' output. 2 factories, running at capacity, could produce over 400,000 Jeeps per year. Japan's entire automotive industry, all manufacturers combined, produced fewer than 50,000 vehicles annually, and most of those were commercial trucks built to civilian standards. The Kurogane, Japan's only purpose-built military reconnaissance vehicle, was being produced at a rate of roughly 4 per day. Total production since 1936 had reached barely 4,000 units. America was building 100 Jeeps for every Kurogane Japan produced. And those Jeeps were better, more powerful, more durable, more versatile, able to carry twice their rated load without mechanical failure, able to operate in conditions that would sideline a Kurogane, maintained by mechanics using standardized parts that were identical across all vehicles, rather than Japan's system where each vehicle required individual fitting and adjustment. Yamashita dismissed Hara, but kept the report. 2 days later, Hara received new orders. He was to locate, acquire, and test every captured American vehicle Japan could find. Not just Jeeps, but trucks, half-tracks, tanks, anything with wheels or tracks. Test them, measure them, determine their capabilities and their limits. And most importantly, determine whether Japan's industrial base could produce equivalent vehicles if given accurate specifications and adequate resources. Hara knew the answer to that last question before he started. No. Japan couldn't produce equivalent vehicles, not because Japanese engineers lacked skill or knowledge, but because Japan lacked the industrial infrastructure to manufacture precision components at mass production scale. The Americans had spent the 1930s building that infrastructure. Automotive factories equipped with transfer line, machining, where parts moved automatically from station to station. Each operation performed to exact tolerances by specialized machines, standardized gauging systems that ensured components from different suppliers would interchange perfectly, quality control processes that caught defects before they reached assembly lines. Japan had none of this. Japanese factories still relied heavily on skilled craftsmen, filing and fitting parts individually. A Mitsubishi engine block and a Nissan engine block, both nominally built to the same specifications, would have enough variation that pistons and bearings couldn't be swapped between them. This wasn't a problem for producing small numbers of high-quality items. It was an insurmountable barrier to mass production. Throughout May and June of 1942, Hara tested captured American equipment across Southeast Asia. In Singapore, he evaluated a GMC CCKW 6x6 truck that had been hauling supplies for British forces. The truck carried 10,000 pounds of cargo routinely, sometimes exceeding 12,000 pounds on good roads. Its engine, a 270 cubic inch inline 6, produced 90 horsepower and could run continuously for 16 hours without overheating or mechanical issues. In the Philippines, he examined a half-track, an M3 personnel carrier. The vehicle combined tracked rear suspension for cross-country mobility with wheeled front steering for road speed. It could carry 13 soldiers plus their equipment across terrain that would bog down any wheeled vehicle. The tracks themselves were rubber with embedded steel cables, a design Japan had experimented with, but abandoned as too expensive to manufacture in quantity. Every vehicle Hara tested reinforced the same conclusions. American equipment was built to standard designs using standard components manufactured to exact tolerances. Parts were interchangeable across all units of the same model. Maintenance procedures were documented in clear technical manuals with exploded view diagrams showing how everything fit together. Supply chains were organized around standardized part numbers that worked across all branches of the American military. Japan's military logistics were chaos by comparison. Each manufacturer used their own part numbering systems. Components from one supplier wouldn't fit vehicles from another, even when they were supposedly the same type. Technical manuals were sparse when they existed at all. Mechanics learned their trade through apprenticeship, not standardized training programs. It was a system designed for a different kind of war, the kind Japan had fought in Manchuria, where small numbers of vehicles supported infantry-heavy forces operating with short supply lines. But the war Japan was now fighting required different capabilities. Island hopping across the Pacific meant transporting and maintaining equipment across vast ocean distances. Every vehicle needed to be reliable, because replacements were months away by ship, if they were available at all. Every mechanical failure meant one less truck hauling supplies, one less jeep evacuating wounded, one less half-track providing mobile firepower. And America was producing these reliable vehicles by the hundreds of thousands, while Japan struggled to maintain production of its existing designs. The industrial gap wasn't just about quantity, it was about systematic, reproducible quality across massive production runs. It was about supply chains that could deliver millions of identical parts to assembly plants without requiring skilled fitters to make them work together. It was about an entire industrial ecosystem designed around interchangeability and standardization. Hara submitted his final report in July 1942. The conclusions were blunt. American vehicles represented a manufacturing achievement Japan couldn't duplicate with current resources and infrastructure. Capturing American equipment provided valuable intelligence about design philosophies and engineering approaches. But copying those designs wouldn't help Japan, because the designs depended on manufacturing capabilities Japan didn't possess. The report recommended against attempts to reverse engineer American vehicles. Japan's limited industrial capacity should focus on designs optimized for Japanese manufacturing strengths, hand craftsman quality over mass production quantity, specialized vehicles for specific roles rather than general-purpose platforms, designs that used materials Japan could produce domestically rather than requiring imports. The response from Tokyo was silence, not rejection, not acceptance, just silence. Hara's recommendations disappeared into the bureaucracy of Imperial General Headquarters, where they competed with hundreds of other reports, assessments, and intelligence summaries. The war continued. American jeeps became increasingly common on Pacific battlefields, captured by Japanese forces, evaluated, sometimes pressed into service with rising sun markings painted over American stars. But Japan never built anything equivalent. The Kurogane remained in limited production until 1944, when bombing raids disrupted component supplies and the factory was redirected to aircraft production. Total production reached 4,775 units, less than America produced in a single week. Japanese forces continued to rely on a hodgepodge of captured vehicles, commercial trucks impressed into military service, and horse-drawn transport. The gap between what Japan needed and what Japan could produce widened throughout the war. By 1943, American industrial output exceeded all Axis powers combined. The numbers were staggering. America produced 300,000 aircraft during the war, more than Germany and Japan together. Produced 88,000 tanks when Japan produced 2,600 across all types. Produced 2 million trucks when Japan produced roughly 165,000, most of them light commercial vehicles unsuitable for hard military service. But focusing on the numbers misses the deeper story. The numbers were possible because of manufacturing systems designed around standardization, interchangeability, and quality control at scale. American factories weren't just bigger than Japanese factories. They operated on fundamentally different principles. Assembly lines with specialized stations, transfer machines that performed operations automatically, gauging systems that checked dimensions precisely, statistical quality control that identified process drift before it produced defective parts. These weren't secret technologies. The principles were documented in engineering textbooks and industrial journals available before the war. Henry Ford had pioneered many of the techniques in the 1920s. building Model T automobiles with complete parts interchangeability. What Japan lacked wasn't knowledge. It was capital investment, industrial infrastructure, and perhaps, most critically, a manufacturing culture that prioritized process over product. Japanese manufacturing culture emphasized the craftsman, the master metalworker who could file a bearing race to perfect smoothness by hand, the engine builder who could listen to an engine and tune it by ear to optimal performance. These skills produced exceptional individual items, but they didn't scale. You couldn't train 10,000 craftsmen in the time it took to design and build a transfer line that performed the same operation automatically on 10,000 parts per day. America had made that investment in the 1920s and 30s. The Depression had provided both motivation, finding ways to reduce labor costs, and opportunity, unemployed workers available to operate new machinery. By 1941, when America entered the war, its industrial base was primed for rapid expansion. Factories designed for automobile production could be retooled for tank production in months. Workers trained on standardized assembly processes could transfer between product lines with minimal retraining. Supply chains organized around interchangeable parts could scale up simply by running more shifts. Japan had none of these advantages. Its industrial expansion in the 1930s focused on military equipment, especially naval vessels and aircraft. Shipyards and aircraft factories received investment and resources, but these industries emphasized custom fabrication and hand assembly, precisely the opposite of what modern mass production required. A battleship or a Zero fighter was built by skilled workers, fitting thousands of components together individually. Every ship was unique. Every aircraft required adjustment and tuning after assembly. That approach worked for producing small numbers of complex, high-performance equipment. It failed completely when trying to produce 600,000 Jeeps, or 300,000 aircraft, or 2 million trucks. The industrial system couldn't scale to those numbers while maintaining quality, and without quality, quantity became meaningless. A truck that broke down after 500 miles was worse than no truck at all because it consumed resources, parts, maintenance, transportation. Before failing, Captain Hara understood this in April 1942 when he tested that first captured Jeep. The vehicle represented more than American engineering skill. It represented an entire industrial philosophy, an entire manufacturing ecosystem, an entire approach to producing machines that worked reliably, because reliability was designed into every stage of production, from raw materials to final assembly. Copying the design would accomplish nothing without copying the system that produced the design. But explaining this to military commanders focused on immediate battlefield needs proved impossible. Generals, they wanted Japanese vehicles that could match American capabilities. They wanted engineering solutions to what was fundamentally an industrial problem. They wanted crashes programs to reverse engineer captured equipment and put Japanese equivalents into production immediately. None of these approaches could work, but each consumed resources that might have been better spent elsewhere. By 1943, Japan's industrial situation had deteriorated beyond any possibility of matching American output. Raw material shortages affected every industry. Steel production dropped as imports from occupied territories were interdicted by submarine warfare. Aluminum production, never sufficient, declined further as electrical power generation struggled to meet demands. Machine tools wore out and couldn't be replaced because machine tool production had been cut to redirect workers to ammunition manufacturing. The cycle was self-reinforcing. Lower production of industrial equipment meant lower production of consumer goods and military supplies. Lower production meant more equipment needed per unit of output as efficiency declined. More equipment needed meant more machine tools, more factory space, more workers, more raw materials, all of which were increasingly scarce. By mid-1944, Japan's industrial output was falling in absolute terms despite desperate efforts to increase it. American production, meanwhile, continued to grow throughout 1943 and peaked in mid-1944 at levels Japan couldn't have achieved even in peacetime with unlimited resources. The cumulative effect was overwhelming. By September 1944, the material balance on Pacific battlefields had shifted so decisively that tactical skill and fighting spirit couldn't compensate. American forces had more of everything: more vehicles, more ammunition, more fuel, more food, more equipment, and all of it worked reliably because it was built by an industrial system designed to produce reliable equipment at massive scale. The Japanese soldiers who faced this material avalanche understood what it meant. They saw American supply dumps with months' worth of ammunition stacked casually because resupply was certain and abundant. They saw American camps with vehicles parked in rows, more vehicles than most Japanese garrisons had ever seen, waiting to replace any that broke down or were damaged. They saw American forces operating with a material confidence that came from knowing replacements were coming, spare parts were available, repair facilities could fix anything, and the supply chain wouldn't fail. Japanese forces operated under opposite assumptions. Every vehicle was precious because replacements weren't coming. Every part had to be conserved because there were no spares. Mechanics performed miracles of improvisation, manufacturing replacement parts in field workshops using hand tools and scrap metal. Vehicles ran on bizarre mixtures of available fuels, alcohol, vegetable oils, anything that would burn in an engine. Equipment designed for specific purposes was repurposed repeatedly until it failed completely and was cannibalized for parts. This wasn't just a problem of industrial capacity, it was a problem of industrial philosophy. American equipment was designed to be maintained by average mechanics with standard tools and standard parts. Japanese equipment, when it could be kept running at all, required specialist knowledge and custom fabrication. An American motor pool sergeant could maintain 100 vehicles using procedures written in technical manuals and parts ordered through supply channels. A Japanese motor pool sergeant maintained 20 vehicles through personal ingenuity, accumulated experience, and creative problem-solving that couldn't be taught or systematized. The Jeep that Captain Hara tested in April 1942 survived the war. It ended up in a storage depot in Singapore, one of thousands of captured vehicles the Japanese army used to supplement their own inadequate motor transport. In 1945, after the surrender, British forces reoccupied Singapore and found the Jeep still operational, still wearing its original serial number, still mechanically sound after 3 years of hard use under Japanese operation. A British maintenance officer inspected the vehicle and noted the examination in his report. The Jeep showed typical wear for its age and usage: worn tires, scratched paint, some surface rust on exposed metal. But mechanically it was fine. The engine ran smoothly. The transmission shifted without grinding. The axles were straight and uncracked. The suspension showed no signs of impending failure. 3 years of tropical climate, improvised maintenance, and operation by forces who didn't fully understand its design specifications had not destroyed the vehicle. That was the ultimate proof of Captain Hara's conclusions. American engineering had produced a Captain 5 machine that worked reliably, not despite difficult conditions, but through them. Design robustness, manufacturing quality, and systematic maintenance design combined to create vehicles that tolerated abuse, neglect, and misuse while continuing to function. This wasn't accident. It was the deliberate result of an industrial system that built quality into products from the beginning rather than inspecting quality into them at the end. Japan never developed equivalent systems during the war. After the surrender, during the occupation, American advisors worked with Japanese industry to rebuild manufacturing capacity. They introduced quality control methods, statistical process control, standardized measurement systems, all the techniques that had made American mass production possible. Japanese engineers, including some who had tried to reverse engineer captured American equipment during the war, finally understood what they'd been missing. It wasn't secret technology or superior materials. It was process, system, organization. The lessons took time to sink in. Japan's post-war industrial development drew heavily on American manufacturing principles while adapting them to Japanese cultural strengths. The result, by the 1970s and 80s, was an industrial base that matched or exceeded American capability in many areas. Toyota and Nissan built vehicles that rivaled Ford and General Motors in quality and reliability. Japanese machine tools competed with American and German designs. Electronics manufacturing shifted increasingly to Japan as companies perfected processes for producing consistent quality at high volume. But in 1942, none of this was imaginable. Captain Takeshi Hara stood in that Nagoya testing yard, staring at a captured Jeep that violated every assumption he held about what was possible with ordinary materials and conventional engineering. His report documented what he'd found, but he couldn't explain it in terms Japanese industrial leaders would accept. The gap between Japanese and American manufacturing wasn't just technical, it was philosophical. And philosophy changes slowly, if it changes at all. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.